In this video, I'm going to talk about the linearization of a nonlinear system. So the focus of this course is on the linear system. So in this lecture, we're going to talk about what if we are given a nonlinear system. So there's a way that we can write a system, the nonlinear system, into a linearized one. However, there are also some caveats. So I talk about that the limitation of this approach later on. So the general idea of the linear system is to write into the system into what we call a state space representation. For example, if I give a very simple system given by y double dot, which is u, so I can sort of define the state variable as x1, x2. For example, x1 is y, x2 is y dot. So I can write down this equation, okay, as x1 dot, x2 dot is equal to 0, 1, 0, 0 times x1, x2 plus 0, 1 times u. So you actually can write this out directly. So the first equation you have just x1 dot is x2. The second equation is x2 dot is u. So that is exactly the equation we are given. So to be more specific, so first equation you get two equations. First one is x1 dot is x2 and x2 dot is u, so which means x1 double dot is u, x1 is y, so y double dot is u. So this is the same as this equation, okay. And of course y is 0, 1, x1, x2 times 0 times u, so this means y is x1, okay. So this type of equation, this type of form is x dot is ax plus bu. So apparently this one, so you can write this one as x1 x2 sort of derivative, okay. So if I define my x, big x, x1, x2, so I have x1 dot, x dot is a times x plus b times u, y is cx plus du. So we call this the ABCD form. So here ABCD are independent of x and u, okay. Similarly, we can also write it in a general form like a differential equation. For example, dny over dtn. So this is the nth derivative of y with respect to t plus an minus 1 and dn minus 1 y over dt n minus 1. This means is n minus 1's order derivative of y with respect to t plus so on and so forth plus a0 times y equal to b0 times ut. This is pretty general form that we usually see if the system is a linearized one, okay. So generally, if I define the state variable as x1 is y, x2 is y dot, xn is dn minus 1 y over dt n minus 1, okay. If we write it that way, and we can write this equation, okay, into the following form, okay, which means x1, x2, xn, the derivative of this vector is equal to, so I have a set of equations. You basically can tell x1 dot should be x2, x2 dot should be x3, so on and so forth. So what is the first n minus 1 equation is just like that. So it's 0, 1 to 0, 0, 0. This is what is happened to the a. What happened to a, and this is the second row of this a, so on. So only difference is the last row is negative a0, negative a1, so on and so forth, negative a n minus 1. And this is x1, x2, xn plus 0, 0, 0, 0. Only last entry is b0 times u. So this one, we basically have n equations. So the first equation will be x1 dot is x2, and x2 dot is x3, so on and so forth, until the xn dot xn dot is a little bit different. This is derived from this equation, okay, all right. And y is 1, 0, 0, 0, 0, and time x1, x2, xn plus 0 times u. So which means y is equal to x1, okay. So means, okay. So this is the typical state space representation for the general system represented by equation given by this general form. Okay, this is a linearized system because typically your a and b and c and d, there can be of course it can be time dependent. It can depend on time, but it will never depend on x and u. So this a and b and c and d, they are independent of my state and also input. It could be a function of t, but it cannot be a function of x and u. Otherwise, we call it nonlinear system. Okay, so here I give you an example showing that it may not be always the case we can write a differential equation in this ABCD form. For example, if I give a differential equation which is y double dot plus y times y dot plus 2y equal to u, okay, here I just ignore all the t. It should be yt dot, yt times yt dot plus 2yt plus ut. I drop the t for simplicity of notation. So our question is, can we write this system into a state space representation with ABCD like this? Of course, here ABCD could be time varying, but it cannot be dependent of the state x or input u. Okay, we can follow the same idea as I mentioned before. Define x1 as y, x2 as y dot. Okay, x1 dot is x2. That's pretty straightforward. x2 dot is, I sort of rewrite this if I do here. So what is x? x2 dot is just a y double dot. If I write it, this is a y double dot. Okay, to compute y double dot, we have to move everything to the right hand side, right? So it's y double dot, which is I move the whole thing to the right hand side. So it's u is, this become negative. It's negative y times y dot minus 2y plus u. Okay, so y is defined by x1, so negative x1, and y dot is x2, so negative x1 times x2 minus 2x1, so this becomes minus 2y. Y is x1. Okay, plus u. Okay. So let's follow the similar approach that we talk about how to write this in the ABCD form to see if we could write in the ABCD form or state space representation. So x1, x2 dot derivative is equal to 0, 1, negative 2, negative x1, so and time x1, x2. Okay, so this one is not unique. You can swap basically because this x1 I have x2, so you actually have different form you put over here. Okay, you can do negative 2, negative x1, or you can do negative 2 minus x2, and this becomes 0. That's also okay, right? But this is one way you can it doesn't matter which way we're using. Okay, let's just use this approach. Okay, and plus 0, 1 times u, because this is kind of the close one we can find out in terms of this ABCD form or state space representation. Of course, here y should be still okay. Y is equal to 0, 1, 0, x1, x2 plus 0 times u. So notice that although here we sort of the structure similar to the ABCD form that I mentioned over here, okay, A and B and C, the difference is we have some of the A and B and C and D. Here is A. A is depends on x, because the A inside we have x1. x1 is part of my state. So which means here A is not independent of x. Okay, so typically when we have something like x dot is A could be a function of x times x plus B times, even if you have one of them, bu and y is cx plus du. Even if only one of them is linear dependent on x, for example, is dependent on x, this is called what do we call nonlinear system. So we cannot use whatever we talk about in the the later slide lecture talking about solutions, for example, stability. All those probably won't apply to this type of nonlinear system. All right. So one of the questions we might have in mind is, hey, since we're talking about linear systems, so what ways can we do to linearize the system? When I mean linearize, so I can write this nonlinear system in a sort of linear system, so I can still apply the techniques we learned in the course to, for example, find a solution, analyze stability, design control, so on and so forth. Okay. Indeed, yes, there's a way we can linearize the system, but also there are some of the limitations I talk about towards the end of this portion, this part. Okay. So let's first talk about what is the linearization of linear system and the basic principle, ideas, and steps. Okay, it won't be covered entirely in this lecture, but it will be covered in the next lecture if this cannot be covered. Okay, so the linearization of linear system talks about how do I write a nonlinear system in a linearized form, which means we still have the ABCD form. Okay, as I mentioned right over here. Okay. So key idea of the linearization of nonlinear system is to sort of approximate the nonlinear function by a linear form. So a typical way we consider this is sort of the Taylor expansion as we typically used to write a function into a set of the sum of set of components. Okay, for example, if I give a nonlinear function, this doesn't mean it's high order. Okay, it could be just a function. I showed over here how different x you can define a function g sub x. Okay, so let's assume for some x0 point I define an x0. Okay, then of course for that x0 we have a specific value which is g of x0. Okay, which is gx of 0. So the Taylor expansion says, okay, if I just deviate a little bit from this x0, for example, this is my new point over here. Let's use different color. But okay, very close to this x0, okay, a neighborhood of this x0. So even if it's a nonlinear function, I sort of can approximate. If I want to figure out the value of gx at this very tiny one, like let's see, this point is gx. This point is x0 plus delta, and this point that is on the function here is gx0 plus delta. So this is the actual value. So the relationship between gx0 delta and gx0 based on the difference between the x0 and x0 delta can be written in this way. So gx0 plus delta is gx0, okay, this value plus dg over dx when x evaluated at x0 times delta plus 1 over 2 factorial d2g plus dx over dx square square evaluated at x equal to x0 delta square, so on and so forth. Okay, well, this means you can write this value as, we can call this base. Okay, and plus some deviation from this value. Actually, the deviation for this guy is sort of linear one. Okay, because if you evaluate, this is actually a constant. Okay, what this means is I take a partial derivative of g with respect to x, and then evaluate that function at this x equal to x0. So this is a constant. It doesn't depend on the state. And this delta is the difference, how much difference this difference is. Okay. This one we have further one is more like high order because the delta is a high order term. This actually is equal because you can do the Statespace. Assume that you are close to the x0. You can do that. Of course, you still have high order one. This you have delta q plus so on and so forth. The nice thing part for this one is if delta is very close to 0, okay? So this delta square is super small, and delta cube is even smaller, much smaller. If you're doing so on and so forth, so this called higher order term is very close to 0 when delta is very small. So I sort of can ignore this. So this is where the linearization is coming from, because from gx0 to gx0 plus delta, if delta is small, you sort of consider this is the linearized one, because you sort of consider this dg over dx is sort of the gradient at this point. At this point, this is gx0, you take a gradient, you find this value, so this is dg over gx0, okay? So that's the actual median. You take a gradient, you find the slope of it. Then when you move along the actual function gx0, it's almost the same as you move along the slope. The slope is kind of a linear function, okay? That's the key idea of the Taylor expansion. In other words, we sort of can see gx0 plus delta is approximated by gx0 plus dg over dx evaluated at x equal to x0 times delta. This is more like a linearized one, okay? This is how linearized. So this is a linearization. You can consider this linearization of a scalar function. Okay, so we can also extend this to a vector form, which will be used later on when we compute all the linearization of nonlinear systems. So this is when we talk about vector forms. This is a vector, which means you have a number. The g has a number of functions, g1, g2, so on and so forth. Okay, so this one can also approximate x0 is in a vector form, and plus partial g over partial x evaluated at x is x0. The only difference is the partial, because you have the g is a vector, x is also a vector, right? So you have a called partial derivative. Okay, I'll talk about this partial later on. It's defined over here, and time delta. So this is still evaluated. This is still this is basically a matrix. Okay, this is a matrix. Okay, and of course it doesn't depend because you value x at a specific value. So this is a constant. Okay, maybe a function of t could be, but it's not a function of state. So time data, see, this is still a linearized one. In particular, we can see here is partial g over partial x is given by this. So I'm going to write over here, x equal to x0. This is a matrix. The matrix is computed as, assuming my g vector is given by g1, g2 over gn. Okay. Of course, my vector x is given by x1, x2, xn. So my g, the partial g over partial x, evaluated at x being x0, is given by partial g1 over partial x1, partial g1 over partial x2, partial g1 over partial xn, all evaluated at x equal to 0. So this is your first row. So first row is always g1. Okay. But when you take a partial derivative with respect to the x1, x2 until xn, that's why you put n entries for the first row. The second one, as you can imagine, it will be you change only g1 to g2, so everything else will be the same. You take the partial derivative g2 with respect to x1, x2 until xn. Similarly, you keep all the rows, you do this until you reach gn. So partial gn over partial x1, partial gn over partial x2, partial gn over partial xn, so on. So you, of course, they all have to be evaluated at x equal to x0. So those are all partial derivatives. Okay. So I assume that this has been you know how to compute a partial derivative. Okay. If you don't know, you can check online how to compute the partial derivative. Okay. All right. Now let's move to the nonlinear function. Okay, what if I have a nonlinear system which is x dot is f, typically written by fx ut. Okay, so here you can sort of consider this being given as x1 dot t is f1 x ut, x2 dot x2 x ut, xn dot is fn x ut. So that will be by n different nonlinear equations, and also y is equal to g x ut. Okay. Now here's something I want to emphasize. Okay, this is a setup of the linear system. It really depends on how we mention what we mention about linearized system. So here's we set up the how to set up the linearization of the nonlinear system. So we set here, given some nominal control, okay, a nominal initial state, x tilde t0, find a linearized system around the nominal control, of course, and the nominal state and the nominal output y tilde t. Okay, so this is pretty similar to the idea that I mentioned over here. We try this, if we consider this is called, if I call this one, okay, this is sort of the, what does the nominal means? So we need to figure out what is my g x0. Of course, here we already give you a function, you can figure out this one directly. But for a system is a little bit complex because I need to, so the nominal over here, it only refers to the output of the g tilde, g of x0. Here the nominal refer to three things, x tilde, u tilde, x tilde, and y tilde. Okay, so this is the idea showing what it means. So this is the figure showing what this really means. So first of all, okay, what this tilde really means. So first of all, I have, let's say for some time, for certain nominal control input, like for certain input, well, I can compute the state based on this equation, right? Initial value, if I give the initial nominal initial value, and nominal control input. If I put it all in all these equations, I can figure out the actual solution x tilde t. Okay, so that's what I mean by if I give you certain nominal control input, and I can compute the nominal state. Of course, when I put this nominal state into x tilde and u tilde into this equation, I get a y tilde. Okay, so I get here is x tilde. Basically, so that's what I mean by nominal. So you give some input, and you get some state, you get some output. Okay, what this linearization of the nonlinear system says is find a linearized system around the nominal control input, the nominal state, and the nominal output, which means your input, if my input deviate slightly from my actual the nominal one, and also my state should also deviate fairly small around my nominal one, and my y-put is also deviate quite small from the nominal one. Now this deviation satisfies the linearized form. So if I define x delta as x minus x tilde, y delta is y minus y tilde, and u delta is u minus u tilde. So x tilde is a nominal state, okay, computed based on the input, nominal input, and nominal initial state. And y tilde is nominal output, u tilde is nominal control input. Now what we can say is x delta dot, the difference here, the difference, all the difference, sort of satisfying the ABCD form. I have an A and B and a C and a D form. Okay, so the key takeaway here is the state deviation, the control input deviation, and the output deviation form from the nominal ones approximately follow a linearized relationship given by this star. Okay, under the condition that if the deviations are very small, x delta or u delta very small, then we can say, yeah, this is true. Okay, so key idea for the linearization of a nonlinear system is trying to say, if I know for some given input, I have some state and output that I can compute based on this input. Of course, I also give some initial values, the initial states. Then the deviation, if the deviation from, if I make a small deviation from the actual input, then we can see the deviation of the state and the deviation of the output satisfy the linearized form, which is the ABCD form. So here the A and the B and the C and D, they are independent of the state and the input. So this is just function, could be a function 2, could be a constant. Okay, so that's the key idea of linearized system. So in the next video, I'll talk about what is this A and B and C and D. What is the actual form of it? And I'll give example showing how we compute the A and B and C and D and how to do the linearization.